Good afternoon and hello everyone, and welcome to our webinar, The Summit, with today's speakers Joe Lstiburek and John Straube. Thank you for joining us for this webinar, which is part of our learning series, Building Science Deconstructed, which is aiming to provide the industry with education focused on better building practices, technology, and building science. My name is Marcus Jablonka, and I work for Dörken Systems as Vice President Operations and Marketing. Dörken manufactures high-performance construction materials. Amongst them are air and water-resistant barriers, rain screen membranes, drain boards for Dörken, for foundation walls, and others. The company has been founded in Germany in 1892, where its international headquarters are. And the North American headquarters are in Beamsville, Ontario, just an hour outside of Toronto. Just a quick word on questions and answers. We can address questions during the webinar. There is a Q&A button in the control bar that you can utilize to put your questions in. There's also a chat function, but I'd ask that you put all questions in the Q&A button so that we can find them there, and we can try and address as many as we can during the session, and some perhaps also during a Q&A session at the very end. In case you miss anything, there will be a recording of today's webinar made available to everyone. With that, I'd like to introduce today's speakers. Since they're the most influential and respected building science experts in North America, they don't need much of an introduction, so I will keep this brief. Dr. John Straube is a professor at the University of Waterloo, teaches at the Civil Engineering Department in the School of Architecture. He's also the principal at RDH Building Science, and he's a structural engineer. Dr. Joe Lstiburek is a principal of Building Science Corporation. He contributes regularly to the ASHRAE Journal. His commitment to education has earned him the hailing the Dean of North American Building Science by the Wall Street Journal. And he is a mechanical and civil engineer. Both John and Joe are researchers, forensic experts, authors, expert witnesses, and extraordinary mentors. And their commitment to advancing the building science industry has had a lasting impact on building codes and practices. With that said, I'd like to welcome John and Joe. Thank you for joining us today. We're excited to have you with us. And with that, I would like to open up the screen and the panel discussion, John and Joe, on our first topic that we want to touch on today, which is whole building airtightness testing.
So the first topic that we're going to spend some time on, the way it's going to work is I'm going to give a short intro, and then Joe and I are going to have some back and fro about the topic, and then Joe's going to introduce the next topic, and I'll do the other one. So this first topic, and obviously what's been chosen are topics of great interest today, things that hopefully many of you on the call will be interested in, and that is whole building airtightness testing. And in some ways, it's kind of funny that we're talking about it because we've been doing blower door whole building tests for houses for, well, a long time. And certainly it was already pretty common in the late 80s if you were in high performance buildings like the vaunted R2000 program that Joe was instrumental in back in Canada in the early 80s. And then it became pretty normal in different types of Energy Star programs and so on. So what's changed, what's different is not the housing sector, not the single family homes. It is the fact that we are now applying this to apartment buildings, shopping malls, laboratories, and hospitals, etc. And not just as a research tool, because a couple by the name of Tamura and Shaw in Ottawa were doing high-rise buildings and hospitals in the 70s as air tightness testing. But because we're now doing it as a matter of course, I could say, in a percentage of high-performance building projects. And so the federal government in the United States has required it for all of their buildings. And so basically, why we would do this is because we're more concerned than ever about airtightness and its impacts on energy, condensation, comfort, and health. And so there's a bunch of reasons why we want to be able to have good airtightness, and there's no reason that big buildings shouldn't get the same care and attention that a single family residential home does. And so there's a number of ways to go about this. Again, in the early days, even the first large building I did, we used the building's mechanical system. There was a special standard for that in Canada. But lately, it's all been blower doors. And partly that's been helped by the fact that standard blower doors can be teamed together, electronically networked. And secondly, the buildings are tighter. So now, you only need 4, 5, 10 maybe blower doors to do some pretty serious buildings. And so that's become the norm. So I'll leave it there about what it is, why we care about it. And I want to say, just turn it over to Joe, just to comment a little bit about maybe the history or why you think it's a fantastic thing or a horrible thing, depending on your mood.
Well, I'm in an extremely good mood, and it could be the alcohol and being locked up with good wine for 3 months. But look, this all started from a smoke and fire safety perspective. And so it's real important not to kill people. And the tighter a building and the tighter the compartments within a building, the safer the building is. And there needed to be some way of verifying whether or not the tightness, the pressure relationships were actually established. And Timur and Shaw were instrumental in this. And this is in the 60s when the Toronto Maple Leafs were still winning Stanley Cups, Sean.
That was a long time ago.
A long time ago. And so it started from the smoke and fire perspective, and then this energy thing suddenly appeared. The Mideast War and the Arab oil crisis and whatever, and all of a sudden, by God, we could actually save a great deal of energy. So the energy came after the fire safety, and then we decided, well, guess what? We're adding an awful lot of insulation to these buildings. The insulation is reducing the energy flow, which means that if things get wet, they stay wet longer. And so it had a durability issue, and airtightness reduced that. And so we started having to deal with the airtightness from a durability perspective. So we went from fire safety and energy to basically durability. And then we decided, well, maybe we ought not to build our buildings out of stupid stuff and fill them with stupid stuff and put people in a risky situation. Maybe we should decide to control, ventilate, and provide air change. And one of the old guys that taught me said that before you can control air, you must enclose air. And so to get it all, we needed airtightness. And then the problem was not how to test it. The problem was where to put the barriers and how good should they be.
And I think actually it's kind of like many of these topics, there are circular parts of it, and we spiral into eventually the right answer. But fire safety and smoke, for example, has largely been forgotten until the rubber hits the road and you find out that the local fire department needs you to do a pressurization test of the elevator core, and you can't achieve it because your building's too airtight. And I had that happen like 5 or 6 years ago. Because the intention of the fire code is that you turn a fan on the roof, it delivers so many CFM into the elevator core, and you need to have airflow out of that elevator core to keep smoke away so the firemen can use the elevator. Well, if the building is really airtight, it doesn't matter what the fan on the roof is doing, it just no airflows. And so then you fail the test. And so there's that's sort of some unintended consequences. But I think the more significant one is that in the goal to get good airtightness buildings, and I'm all in favor, and it's actually happening, is that people forget this HVAC interaction side, the ventilation side. And the first and obvious step is that they don't properly ventilate, and you only notice that when you finally have an airtight building. And so now you end up with bad air quality, not because you made the building airtight, but because you didn't have a good ventilation system, and the weakness is now visible. And the second aspect is that the mechanical systems are not at all integrated with the enclosure. And so then you end up with buildings that are supposedly pressurized by the mechanical engineer, but because you built an airtight building, the pressures are stupid and you get whistling noises and the front doors blow open. And so while I think it's important that people are interested in whole building airtightness, and it's great that we're starting to do it. The value of having a real number on the test is that we can go back to the mechanical engineer and saying, okay, this is what you're designing for now. And until now, most mechanical engineers designing for pressurization, they guessed. Like, how much do I put in? How much air do I put in? Well, I don't know. How leaky is the building? Well, I don't know. I've never measured one. So I think that's going to be pretty profound, is that it'll be normal for people to know how leaky their buildings are. And therefore you'll be able to design your HVAC to properly work.
John, quick question on that. Maybe you can help quantify that a little bit. I think these days most people are pretty much on board, most people, that more airtight is good or better. But can you maybe elaborate a bit more on what is actually a good number, and how practical is it to achieve that number?
Well, okay, I'll tell you, depends what number you want to hear. I mean, because really it isn't a precise number, right? People choose numbers, and that depends on which room at which time the numbers are chosen. But it's difficult to provide a scientifically based number that says you should be down at least this tight. I suppose some people would argue the tighter the better. 0 is the goal. Well, I mean, in theory communism works. In practice, I think we definitely want to choose a reasonable number of air tightness, and if we can do better than that, great, but be aware that there are consequences to being better. So what are those numbers? So the numbers that the General Services Administration chose with coaxing from people like Joe and I was that they stole the numbers from the Canadians who pulled a number out of their butt in the late 1980s. And that number is something like 0.4 CFM, cubic feet per minute, per square foot of enclosure area at 3 inches of water column. Those are imperial numbers. Metric numbers, 2 liters per second at 75 pascals per square meter. But those are not holy numbers. When we get to those numbers, experience, and I want Joe to chime in on this, but it seems that you get a noticeable change in performance. The buildings start to actually behave more predictably. You avoid major catastrophes and condensation, clear energy savings, comfort benefits. But clearly, you can easily get twice as tight, and it would be good. But when you get 10 times as tight, you start causing problems. And we haven't yet totally made that shift in our building systems. And the problem I normally point out is that if you get really tight, you slam the front door, the toilet flushes, and so you waste water. And so there's obviously, or you turn the range hood on and your windows implode. So you got to find the right spot where a little bit of leakage isn't bad, but obviously we want to get tighter than those standard numbers. So Joe, I just thought maybe you should comment a little bit about where you think the targets are going and should be.
Well, I think we're already tighter than we really want to be. There's no justification for the passive house levels of tightness. The original number, I was a 26-year-old, and the guy taught me, he said, "Young Joseph, we need to set an air barrier material limit." And I said, "Okay, what do you want me to do?" "Go out and measure the air leakage of 10 sheets of drywall." Well, I could only find 7 sheets of drywall, and so the 0.02 came from me testing 7 sheets of drywall in 1982. And then I simply multiplied that number by 10 to get the air leakage of an assembly, and multiplied that by 10 to get the air leakage of an enclosure. It was a giant freaking guess. And the fact that suddenly it has become a holy number that's a pun, you see, a holy...
Or not holy, depending how you look at it.
And the idea is that the intent was always to get rid of the big holes so that the small holes wouldn't matter. I want to build on something that you've introduced, and that is, it's completely changed the way the mechanical systems are having to be installed and operated. There's no way when you compartmentalize an apartment building that exhaust-only ventilation with central systems functions. It has to be balanced ventilation. And that's just an incredibly difficult concept to get across. And picture this, no vented dryer now functions. You turn on a dryer at 200 CFM, you're gonna basically be able to suck a golf ball down a garden hose a mile long. I mean, you get 30 to 40 pascals of negative pressure. So we don't have dryers that work. Try installing the typical 400 or 500 CFM kitchen exhaust fan. So we don't have exhaust fans with makeup air that are interlocked. We have them in kitchens and commercial spaces, but we don't have anything residentially. But we don't understand the need for balanced ventilation and distribution in tight apartments and in tight houses. So we don't have the appliances. No exhaust fan works. If you have an exhaust fan, you know, you need to have supply. I mean, and the mechanical engineers are not quite there. I can say that as a mechanical engineer as well. I mean, I'm schizophrenic between the mechanical engineering and the civil engineering. I mean, thank God I'm not a structural like you. And
well, then you'd have problems.
So, but this interaction of the air-consuming appliances in a building and the tightness is changing everything, and we're behind. The industry does not appreciate the issues.
And just because somebody asked a question about the values that we're using, these target numbers. Let me just say, go to buildingscience.com. There's a Building Science Digest or insight on air barriers or air tightness, Joe, where he talks about understanding air barriers. And it also provides some good examples of how this air tightness, although we're talking about a whole building, really it could be a whole apartment suite, or it could be a single floor in an office building. And the reason I mention that is that air tightness testing is easier if you can break the building down into units, whether it be, you know, apartment units or office floors. But B, because the benefit of air tightness is not just between the indoors and the outdoors, it's between you and that horrible tenant next door that has a meth lab. And so being able to separate between units is actually, I think, something that hasn't been appreciated enough. I mean, as a benefit of an air barrier. And I know, Joe, you've definitely pushed a lot on multifamily housing to get that air tightness between units. And frankly, by fire rules, we should be airtight. But when you test them, we're not, which tells you that we should be doing some effort there.
And I'm going to say that this is my last comment on saying I'm going to do a prediction here. And I'm not very good at predictions, but mechanical engineers are born with a genetic defect. It's the integration and central big piece of equipment gene. And it reminds me of the fight between central computing in the university days and laptops.
That's right.
And guess what? The big central systems lost to the laptops, and I'm here to tell you that the individual ventilation systems and compartments are going to defeat the central systems. So we're going to go to distributed individual small pieces of equipment rather than big monstrous things that nobody understands how they operate. So that's my prediction.
Thank you, Joe. You commented on the interdependence that we need to understand better between different factors affecting air tightness. Could we go into some more detail on the context of the changing way we build? So conventional on-site construction versus, say, mass timber buildings versus modular construction. How does this affect air tightness, and what do we need to keep in mind when testing it?
I think I'm not convinced that modular construction accomplishes very effective tightness because people haven't figured out how to connect the modules to one another, and we end up with these complex three-dimensional airflow networks that don't accomplish a heck of a lot. So
it's all about the joints, and as many know from the whole debate, but also what's those modular construction by its nature, which is distinct from panelized, there are often gaps between the modules that end up being built into the building. And while that doesn't affect the overall building air tightness, it does affect Joe's comment about the three-dimensional airflow networks. And you actually build air gaps between neighboring units and between the floors above and below those units. And those are built into the building, and very hard to not have them be air permeable. And so you can get some really interesting unintended consequences that aren't nice by having those three-dimensional airflow networks in modular. In panelized and modular, it actually, the focus on air tightness is key. I mean, and so getting those joints sealed, it's just not easy. And whether or not they're passive house tightness or just GSA US tightness numbers, that's where you end up with mistakes. That's where you have to design properly and then build properly, because they are really leaky.
I've come to the conclusion that I can't rely on a single seal. I've come to the conclusion that I need two-stage joints, and then I assume that they fail and design a method of the building surviving. I learned this back in the early days of structural insulated panel roof failures in the joints. And you know, I call it faith-based air sealing. It just, you have to do the best you can and assume that there's going to be some leakage, and the design a means of forgiveness for that leakage to occur.
Let's move on to the next chapter here, mixed use and multifamily buildings. Can we dive a bit in the discussion? What are the trends here, and why are they special?
Well, I've been quite surprised in the last 10 years how much part of the sector of the industry has increased. I call it podium construction, where the first floor is typically commercial and institutional space, and it's, you know, it's steel construction with concrete columns and an elevated concrete slabs. You've got a slab that's elevated 20 feet above grade, and underneath it you've got restaurants and office space and everything you can think of from the commercial sector. Then on the top of that, you then add 4 or 5 stories of wood frame in a courtyard. And so you've got ostensibly the combination of the best commercial design on the first level, and then the best wood frame approach on the levels up above. And of course, being the cynic that I am, because of what I've seen, I think we've ended up with the worst of both, the worst of the commercial and the worst of the residential. And so, these podium projects are all over the place, and the riskiest failure is the waterproofing and the water control of that elevated slab. Because what do we put on that slab? Every conceivable water hazard known to humanity. Let's put a swimming pool there. Let's put planters there. Let's put, fountains and whatever. Let's put doggy walks. And then let's have, Neiman Marcus and, a big expensive restaurant underneath. If you get a leak, it's the end of the world. And we've had to relearn how to waterproof. I've tried, trying to explain to people that you need to slope the decks. Don't be a dope slope. Our stuff is so good. It's so waterproof. We can just put it on flat. It's just freaking wonderful. I'm saying, well, I think you're an idiot. We should have drains and slope to the drains and whatever. With the wood frame up above, architects have genetic defects. They're called the innie, outie, and tweenie genes for windows. The windows are inset in the walls, and it's like an incredibly convoluted facade. And literally everything leaks rain. It's like, you're kidding. And so, after having failures with respect to waterproofing the deck, window leakage and deck, let's also decks. Let's put every conceivable bad thing that we can from a water perspective and multiply it by hundreds of units in the same project. So everybody gets a deck, everybody gets a sliding door, and the sliding door is value engineered. And of course, there's no value in the value engineering. And so the failures have become rampant. But the good news is that people are now saying, well, my God, we need to water test all of the windows. Okay. We need to water test the balconies. Well, okay. And I'm saying, well, all right, so we're now handling the decks and the balconies, but you realize you've got 200 units. Where are you going to put your mechanical systems? And we've not yet been able to fix the mechanical conditioning part of these projects. I know that this is, I'm belaboring the point based on what John and I talked about in the first section, but we've got literally the combination, the coming storm or the worst storm or the, however, whatever phrase we're going to use. So we're dealing with incredible water control issues, we're dealing with air leakage control issues, and we're dealing with mechanical control issues. And we don't have the skilled trades available to us to execute all of these things.
Well, in fact, one of the reasons that these are seen as desirable by developers is that they can use the single-family residential home trades to do the wood framing or the window setting or the drywalling. And except for that, they're not single-family residential. And so getting the trades who can make that transition to actually, this is getting like pretty much the same as a high-rise apartment building performance quality, means you got to be a little different. But I think I'm seeing the same thing as you are, Joe, in that there's been enough failures, or the word's getting out there to developers, that they are aware that they need to put extra effort in. And the extra effort that you're describing does nicely segue from the first session, is that you at least have to do some mock-up testing. And you're mentioning water, but obviously air would be useful too, right? And it's literally the decks, the doors, the windows, how about half a dozen range hood exhaust, dryer vent exhaust, etc. And, depending on how litigious your clients are expected to be, maybe you have to test 50% of them, or maybe you choose 1 in 7, like Energy Star or something like that. So, but I think that what that says is it's quality control becomes more important, because everybody will sue you, as opposed to only the problem units in a housing subdivision of 200. 10 houses go bad. I'm a big boy as a developer. I can handle that. But when you get 10 that go bad in the apartment building, well, everybody knows the homeowner association suddenly has 200 people who can put their money into a hat, hire a real lawyer, and make you actually fix it. And I think it changes the dynamic.
Well, what's very interesting to me is that the failures have become so rampant that the people who finance these buildings, the banks, now have building science divisions in the banks. And when Wells Fargo and Citibank say, "We'd like you to talk to our building science group," I'm like, "Huh? You have a building science group?" And they said, "Well, yeah, as a matter of fact, we do." "Well, why?" "We're putting up the money, and if the building doesn't work because of silly designs or poor execution, we're on the hook." And so the finance people and the owner developers are now recognizing that they have to put in a great deal of effort at the beginning of the project to execute the correct quality control. But the quality control is not just testing. If you do the wrong thing right, it's still wrong. So, what you want is you want to figure out what the right thing to do is. And that's basically the appropriate design. And then you want to execute the appropriate design on a repeatable basis using the available skills and trades. And what's kind of nice is that in the last couple of years, we've seen some wonderful evolutions in terms of products. I mean, you'd have a 20 or 30 step window installation approach because of, peel and sticks and the window being an innie rather than an outie. And now we have fluid applied. We've got water control layers that are no longer mechanic and air control layers that are no longer mechanically attached. We have stuff available to us today that we're turning it around, but like most of these things become intolerably bad, and then we step away from the edge of the cliff. But boy, I mean, I know the view from the edge of the cliff is pretty darn good, but I like to step back a little bit from the edge.
Yeah, and I think that's why it's you went back to the design, not just the construction quality control. So obviously design quality control is the least expensive quality control. But of course, I mean, I'm sure Marcus can tell us about how Delta does quality control for the materials. I mean, you wouldn't be making a membrane if you didn't have a pretty intensive quality control process for how every roll comes out the door. And what we're learning is that, well, of course, we need to do that in buildings as well. Now, one answer is this interest in prefab. But actually, that's only, there's no reason you can't do good quality control from design to construction on site. It's just that people just haven't chosen to spend the money to do that. And the material side really is at the beginning. You would normally think you start with the materials, then you do the details, and you do the building. But actually, it isn't that way at all, because it's the shape of the building and its occupancy and its climate that decides on what kind of details should I consider. And then we start picking materials that can perform in those types of details. And I think, Joe, the point about fluid applied and fully adhered is classic. We also have gap membranes now, so that how do I put stucco on a wall and still have a gap? You can get products for that now. So there is a response. Maybe we'll get windows that don't leak. That could happen too, but not that I'm holding out for that.
Well, John, my observation is that as people in windows get old, we leak. You youngsters have no idea what's coming.
It depends.
So I would like to tie this back one more time to our first chapter with a question from the audience here. So on how to do it well, with what resources to do it, but then also what really to aim for. An audience member here is asking, are you saying super tight construction is not good? I thought the mantra was the tighter the better, even though there's diminishing returns. You just said passive house levels of tightness are not good. Can you go more into that?
Well,
yeah, Joe, do that.
I was the one that started that, and I'm saying that the passive house levels of tightness are basically a lot tighter than I think they need to be. I don't think that they're bad. I just think that you don't need to spend the resources in order to achieve that. Now, I adore the passive house folks because they're being constantly told that they can't do these things, and they go out and they figure out ways of doing things. They're the rebels, and I used to be a rebel once before I became an old conventional kind of
old and stodgy and boring, yeah, like you are now.
So I love hanging out with them because they remind me of me when I was a youngster, and I want to be them because people kept telling me for years, you can't do that. We all went out and did it. So they're being told you can't do that, and they're going out and doing it. And I'm saying, well, I don't think, 0.06 ACH at, 50 pascals is necessary. Between 1 and 2 is fine. And oh, by the way, your biggest problem is no longer the tightness. Is what are all the air-consuming appliances that you have in your freaking building doing? How are you going to make that work? Well, we're going to ban gas cooktops, and we're going to not have exhaust ranges. We're going to have recirculating ranges.
Oh, Joe is frozen. Joe is frozen. Well, while we wait for him.
And actually, I think that's actually a point where I would say in general, Passive House is really doing good things for the industry and making them ask tough questions about presumptions and setting demanding targets on specific aspects of comfort and energy. So that's good. But actually, that idea where Joe describes how, well, I got it so tight I can't use a range hood because the range hood can't get in the air to exhaust, so we'll go to a recirculating hood. That's when it goes bad. Now, that's not Passive House that went bad. That was a designer making a bad decision to sacrifice indoor air quality so that I can make my 0.02 ACH house work. So it's just, and that's where we need the solutions. And I think that's where, lots of the Passive House communities are, asking, how do we make clothes dryers work without forcing consumers to use different types of clothes dryers, or say, oh, why are you running a clothes dryer anyway? Don't you know that you should be saving energy? Like wear your wet clothes. Or recirculate the oil that comes off your stove. Why do you need to throw it outside anyways? How wasteful. Like, why would you flush your toilet when you could just spin it around? A recirculating toilet sounds like a great idea. So I'm just saying, there's a few cases, and I think they're pretty few, where the argument comes out that trying to meet one Passive House target affects others. Another example is, let's put all the insulation over the window frame, right? So you actually wrap the window, meaning Oh, so now how do I drain the water out, and how do I replace the window in 25 years when the seal goes? Oh, we're not going to think about that. We just need to meet the number now. And, so those are kind of issues where in any program that's aiming for a lot, you're going to run into some friction.
So maybe we can move it along to another chapter or another topic in the design community. At times there's a desire to design buildings with cladding that leaves joints, open joints between the cladding panels for optical reasons. Perhaps mostly this is often happening in multifamily housing in commercial buildings, but really can happen in any type of construction. So the question here really on those air gaps in facade, so the air gaps between the cladding panels, are they a big deal?
Yes. Yeah, they're a big deal, and that's why people want to do them. So you're talking about, we have panels that come together, and in the good old days, when people died at 40 with no teeth, we would put mud or mortar into those gaps. Over time, we started to fill those gaps with sealant because it was easier, right? Some sort of caulking or some sort of silicone polyurethane. But it became pretty clear that, well, if you put silicone or polyurethane in those gaps, you now have to actually replace that and maintain that, which would be a horrible job. And so the idea came about, as far as I know, in Europe in the 60s, about leaving the joints open. And this aligned well with the idea at the time of we're trying to get more ventilation behind claddings, and acknowledging that, and this is a big step, right? It was the first step in a 12-step process. I acknowledge my cladding leaks. So once you say water's going to get past my cladding, well, then it wasn't as big a intellectual jump to leave those gaps open. Now, that said, by leaving the gaps open, it does change a lot of things. You get a lot more airflow behind the cladding. Absolutely. You get less, you don't have to maintain those joints. Yes. However, you may be surprised to know that if you have open joints, more water gets past your cladding than if you have sealed joints. And so that means that the cavity behind the cladding and the water resistive barrier needs to be able to be managing much more rainwater. Another thing is that now that the joints are open, things like the sun can get in. And so now the layer that the sun strikes behind has to be UV resistant so that you can meet the promise of low durability of a long time. But you also have to worry about more mundane things getting through the cracks, like children's fingers. So in school projects or shopping malls, little fingers stick in there, and insects and animals of all types get in those joints. And so there's just it's not just a simple matter of saying this cladding can have open joints. The final thing I'll just mention, because this is just an introduction, but the final thing is that those joints, the horizontal ones, collect water on the horizontal edge. And this is actually one of the things that meant that although there was a burst of activity in the 60s in various type of cladding projects in Europe, how it all of a sudden came to a slowdown because the top edge would capture and water would sit on it, and you'd get staining, either from water absorption or mold and algae growth. And then it didn't look as good. And so it took us a while to figure out, well, what can you do about what cladding types? What can you do about joint design so that those top edges don't retain water? And so there's real advantages to those open joints if you want high ventilation and durability of that joint material, meaning not having one. It's saving money that way. But it changes a lot of stuff. And so it's not a one-for-one replacement. You got to rethink the whole design of that assembly to acknowledge UV, insects, fingers, more rainwater, etc.
And fire, baby. Fire. Have I mentioned the word fire?
It's a hot topic.
It burns me up, John.
Man, someone's going to flame us here.
I don't know what you've been smoking, man, but the presentation's been... All right. I like back ventilated and drained cladding systems. But like most things, it should be in some level of moderation. And in terms of the insects, I was told by one of the legends way back when, and he said, you know, the insect kingdom and the animal kingdom will always defeat the physics kingdom. And I'm now struggling more with insects and animals getting in behind cladding systems than I am having to worry about ultraviolet light, water, and heat. And I know that's kind of bizarre, but
well, we have clear answers to the physics thing because we're building physicists. And I guess we just don't have as good a sense of what the laws and rules are for those biological components so that we can design against them.
One of the things that I've been finding is that the drier it is back there, the less likely I get actually insects.
Absolutely.
And so, but like most things, I like a lot of ventilation, but I don't like a lot of rain, because if I get a lot of rain, I get a lot of wetness, and I don't want wetness, but I do want ventilation. I want dryness, and then, you know, I'm finding that I want to be less than 25 millimeters. I want to be less than an inch. I want to be, if I'm around a half an inch to 3/4 of an inch, I'm not in a bad fire range, because of the friction of the boundary layer airflow is sufficient that I don't have that much of a fire risk. But we haven't got it all figured out after a half century.
Right.
But I feel more.
And I think, Joe, I think it's important that, because it doesn't appear clear to most of the industry. And this is another one of those bigger isn't better. I mean, we're saying more airtightness isn't, you know, there's a limit to how far you want to go because it creates other issues. It's the same thing with that air cavity. There's lots of products being sold in the market where they're saying, oh, that 2-inch air cavity, man, that's really great, or 3-inch. And actually, there are consequences to that. And fire is one classic one. And, you know, can you imagine a 3-inch gap behind, I don't know, terracotta in New York City? That 3 inches, you can rent that out as an apartment. And so there's now enough room in there. If you think just rodents are going to live in there, New Yorkers will live in there. And so getting the gap down, actually, we have to find the magic spot where, and I think I'm with you there on the 1 inch. It's hard to understand why you'd ever want more than 1 inch, because that also means that only a certain types of animals can live in there, right? It's not a good spot for many animals, but 1 inch is more than enough for drainage, and it's pretty good for ventilation. So,
no, I'm with you. Plus, I'm more polite than you about this. I view the real estate as being, the airspace real estate is very valuable. We could put something in there called insulation, John.
Well, that'd be crazy, man.
Amazing thing that could go between the cladding and the rest of the wall assembly. I mean, who would have thunk it? Well, you know, somebody told me about wearing the sweater rather than
not eating it, right? And so the thing about is that it's not an all or nothing. And so if a designer comes and asks and says, hey, I want open jointed cladding, I would never say, oh, that's a bad idea. It's all about, okay, how do I respond? Well, one of the things is that, have you considered a baffled joint? Meaning, so you have a joint, but behind it, hidden from view, is a baffle, often made of black painted metal or something like that. And so that baffle deals with essentially all the rainwater increases, all the UV, most of any bug issues, et cetera. And yet from a maintenance-free and aesthetics point of view, it's identical. Maybe even better.
I think it's a great idea, but it's baffling to many people.
To many, it's baffling, yes. So there's more, as we used to say in my household, there's more than one way to skin a cat, although none of us ever skinned cats. And so there are open joint cladding systems. Well, there can be a whole bunch of different variations on them. And again, what they discovered as one of the solutions for at least the stone claddings in Europe was to get that open gap to be smaller. It's like if you had it down to, say, 3/8 of an inch or 9 millimeters, and the stone itself is an inch thick, well, yeah, you had a little bit of UV, but you solved a lot of the other problems. And so here's an example where, you know, a smaller gap could be better than a larger gap. And that's why It's just something we haven't got figured out yet. We're getting some experience, you know, the last 30 years, but it shouldn't be taken lightly is that if you go open jointed, you probably have to think about a lot of things, including your WRB and, you know, insulation and cladding attachments and edges being exposed to freeze thaw damage and algae growth, et cetera, et cetera.
We call them Lauren Hutton designs in the United States.
I don't get that. I don't know who Lauren Hutton is.
You're obviously young. You don't remember the famous model that had a gap tooth.
No, I don't. No. That's good. I can imagine, though, the gap tooth thing. I can get it.
So Joe, in that context, a question. When we talk about a true open joint cladding system, so not a baffled, but there are real open joints. In many areas, the code is clear and requires continuous insulation. That pretty much defines the location of the thermal control layer. But when we think of the water control layer and the air control layer, from your perspective, what is the ideal location there in a true open joint cladding system?
Well, I like multiple systems redundancy. I like to have a water control layer behind the thermal insulation as the last line or final line of defense. And I'd like to shed and try to prevent as much water from getting through the insulation system as possible. And so I like to have two. I like to have one behind the insulation system. I like to have another one that does, well, not to be perfect, but it provides a great deal of rain shedding on the outside.
And so, Joe, let me just, like, for example, one of the things where, I mean, lots of people ask questions about some of those house designs that you did, say, 10 years ago with polyiso, and you taped the joints in the polyiso foam. Not always because that was the primary air and water barrier, but because that was your outer layer of rain shedding and wind washing resistance. And then you can put a full air barrier behind it or a full drainage layer behind it if you want to. And in commercial construction, that becomes, I think, more relevant as you get to higher exposures. This rain shedding on the face of the insulation and full air water barrier behind it makes more sense. And by exposure, well, open jointed claddings are high exposure. So if you're building 3-story open joint in Maine, I want another layer on the outside of my insulation. But with its closed joint, you could, but it wouldn't be something I'd want to spend my resources on.
I totally agree with you on all of those points. Enjoy the moment. I've totally agreed with you on all of those points.
We're in violent agreement.
So while we have agreement, I'd like to move us on to the next topic and see if we can find it there too. Building codes. Can we perhaps have some discussion on how do Canada and the US differ with regards to air, water, and vapor barriers or control layers?
Yeah, Joe.
Well, I'm much more impressed with the American code making process than I am with the Canadian code making process. The American code making process is a lot more open. Normal people like me don't have to be appointed and voting members of anything to make changes. And so the process is open and virtually anybody can provide a code change. But like most things, there's also abuses. The abuses are, you've got special interest groups that are able to lobby and influence code changes. The Canadian codes are not as susceptible to special interest, but on the other hand, the Canadian codes are not as easy to change, and I don't believe are as easy to deal with problems. The last point, and then I have to open it up, of course, is that the United States has got an insanely diverse climate. You've got hot, humid, hot, dry, cold, wet, ultra cold, everything in between, high wind, no wind, lots of sun, no sun, literally, air conditioning dominated to heating dominated. It's crazy. And in Canada, everybody lives within 100 miles of the American border, and that's historic because that's where the best TV signals came from before cable TV. So, everybody lives this narrow band, and it's easy to have a national code and figure stuff out. In the United States, America is full of diversity, John. in fact, there was some marches lately. And I would assume that they were marching because of the code diversity, not and climate diversity, not because of anything else. But so the process for code change in the two countries is very, very, very different. I want you to know that I took a lot of the Canadian code language, and over the last 25 years, I've surreptitiously inserted it into the American code side. And I see that the Canadians are picking up some of the American code changes as well. And so it's been nice, but I've been finding that the ability to affect change in the United States is a lot easier than it is to affect change in Canada.
It has to do with the size of Canada. It's so much larger. It's just more unwieldy, Joe. That's why.
Well, we have the internet, John.
So, well, on some specific topics, though, I mean, for example, I could say there's a clear superiority in the U.S. code, in the residential code particularly, about vapor control. And I'd say that with a little bit of vested interest here because it was somewhat involved with helping, but Joe was very involved. And it was also came out of a lot of years of frustration with, there was a, 6 mil poly, one number, didn't matter. Everybody assumed it had to be the same all the way across Canada. We're not far different than that today in Canada, and the code certainly hasn't changed. In the United States, the code has changed to saying there are multiple levels of vapor control. It depends on where you are in the country with weather, and it depends on how much insulation you have on the outside. These are all based on science, and it is more complicated, but it happens to be correct. And that to me is one simple thing to identify between the codes that Canada is literally now behind on. But I would say one of the things I think is quite good about the Canadian code is its clarity of how it aligns well with building science, in that it says, there's part 4 is structure and part 3 is fire, and then you have in part 5, the enclosure, we talk about rain is separate from air, is separate from vapor. And these are things that, of course, we use as teaching tools to break down how we need to look at different problems. And the building code in Canada explicitly has sections on, it doesn't say air barriers and then talk about vapor permeance. There's none of that confusion. It says there's air barriers and it talks about air movement. And in vapor barrier section, it talks only about vapor diffusion. And in water, it actually or rain, it talks about like rain. And it doesn't get them all confused with language that is difficult to understand, about using words like weather barrier. Luckily, that's been out of the code for 20 years now, but or 17 years. But anyway, I think that there are real benefits to how it's set up intellectually in the Canadian code. But unfortunately, because of the reasons that you mentioned about its ability to respond to outside influences, the lack of ability in the Canadian code, it hasn't been as responsive, I think, as the American code, which has to, IRC has to administer 10 times as much construction over a more diverse climate zone. In many ways, they're doing it better.
Well, it's funny. I really like, and I'm going to support your distinction. I really like the clarity in the organization of the Canadian code language. I just don't like a lot of what that language is. I like the way the American code is more flexible and has better technology. But man, it's so colossally difficult to understand because it's cluttered. It's cluttered and it can be confusing. So I think what should happen is, John, the Americans should get you to rewrite the American code, and the Canadians should invite me back to rewrite the Canadian code. And I think it'd be a nice exchange. You could spend 20 years down here, and I could spend 20 years. I don't think I have 20 years, but it took 25 years to change the vapor barrier stuff in the American codes, John. I'm done with vapor barriers. Okay, that's we need youngsters.
So I have one quick question to both of you. If it were all up to you and you had full control over it immediately, what would be the one code change you would propose and want to do right away?
Well, for me, I would require balanced ventilation in all occupancies. And I would, as part of that, I would require all air-consuming devices need to provide their own air. So that's what I would do. And I'm coming at it from a mechanical engineering perspective because that's my original roots. And I mean, I've had a lot of fun in the years saying that the problems that we have today come out of solutions that we created for other problems. So the cause of problems are solutions. Yep. So we've solved a lot of problems, and now we've created a whole set of new ones. And it's the mechanical engineering side, the mechanical performance side, that now needs to adjust.
So one of the things that, given that you're telling me, Marcus, I can make one change. I'm thinking about the one wish, which is my one wish is to have more wishes, but apparently you're not going to fall for that trick. So I'm thinking, how can I make a change in the code that has the most impact on the biggest things? I guess I would like to say that notwithstanding any authority having jurisdiction, scientifically defensible decisions will overrule that person. Because although we have a code that says that the authority having jurisdiction can ignore the code, we don't have a building code that says that you can ignore stupid code officials. And so I'd like to see some balance there, is that if there's science, like you can't just say, because in my county, everybody's got to have a vapor barrier on the inside in their air-conditioned bungalow. And it's like, I think that's a bad thing for the country. So that's my one big sort of code that has the biggest impact.
John, I learned how to deal with that in Chicago. $100 cash, and you hire the building officials' relatives to do the work.
It's true, although the price has gone up, Joe. I just have to point out it's no longer $100. Well, not a technique I'm not unfamiliar with.
So, John, I would have gone with your wish for more wishes, but since we're almost out of time, we have to leave it at that one. But I'd like to briefly move into a Q&A session here to address some of the questions from the audience. And I'll read one. It's a little bit longer, but I think it's quite interesting. It will have value for many others as well. An audience member says, as a home builder, I have come to learn about the importance through making mistakes and then trying to stand by my product and systematically find the source of the problems. The question I have is there a significant difference on the importance of the air tightness or performance from one climate region to the next? I understand that there are differences between climate zone 6 and 1 or 2, and the approach for both of these may be very similar indeed, but from dealing with almost polar opposite interior to exterior climate conditions, where do the climate zones 3, 4, and 5 stack up in importance to get this right from an air quality, durability, and performance standpoint?
I don't think we should let that person ask any more questions.
Yeah, that's a good one. I mean, it's obviously informed.
So let me take a short run at it and say that, believe it or not, air leakage from the inside out in a cold climate is important, and air leakage from the outside in a hot climate is important. And when you have mixed climates, air leakage from the inside out and the outside in are important. And I don't see that there's a big variation in terms of the performance requirements for air tightness in climates that have a lot of humidity in the outside air. When you get to places like Vegas, you can pretty much do anything because what happens in Vegas stays in Vegas.
No, but again, I think that's actually important. We say 3, 4, 5. It does matter. Are you talking 4A, B, or C? Because if you're dry, the lack of large temperature differences means that air tightness is less important for those climate zones, for sure. But if you're humid, it's really important, and you can't get away with too much. But the other thing is that you mentioned climate zones 3, 4, 5 in your question. I think that when we look at air leakage condensation problems, the indoor environment is the thing that varies more dramatically depending on the occupancy, HVAC design, and building design than the outdoor climate. And so, and say zone 5, you'd say, well, it's not that cold, it's a little cold. Well, if somebody doesn't have proper ventilation and you have 6 college-age students living there during a pandemic, the relative humidity goes crazy high, and suddenly small air leaks that wouldn't normally affect you become disastrous rot in the wall. And similarly, if you have an air-conditioned modular home over a vented crawl space, it actually, in zone 4, doesn't necessarily cause a lot of condensation problems in the summertime, unless you run that house at your air conditioner set at 67. And then 2 years later, and your floor rots out and you fall into your crawl space. So while the outdoor climate zones are really important and a major innovation in the last 30 years, thanks, Joe, the indoor climate really has to be kept. You got to keep your eye on that as well. And it's harder as a designer because we only have a certain amount of control of what that indoor environment is. But whatever control we have to take it, because that's one of the ways to avoid moisture-related problems due to air leakage.
In terms, I fully agree with you again, John. This is going to be crazy, agreeing with you all of these, throughout this presentation. So I got to get over this. But in terms of the internal environment, we do a lousy job of educating the people who are in the internal environment how they should operate the internal environment.
That's right.
But you can't drive cars a certain way and have their warranty work. You can't drive a house or a building a certain way and have it work. You can't take and operate a house at 67 degrees Fahrenheit in Atlanta for most of the summer, even though your air conditioning system might be.
But you can, but now you have to buy a different house than what most people are buying.
What I'm getting at, you have to design for those conditions. And so a car gets an operator's manual or an owner's manual. We ought to be doing a better job of telling people how they need to drive their house. And if they want high performance, I want to be from 0 to 60 in 3.1 seconds. Well, okay, you're going to need like really good tires, you're going to need really good brakes, and you're going to have to do a whole bunch of stuff differently with your engine. You're not going to be able to do that with, a typical automobile. Well, I can't drive my house at 65, 66, 60 degrees Fahrenheit for 3 or 4 months of the year under these conditions unless it was designed for those conditions.
Or 60% relative humidity in January in a zone 5 Kansas or something. Like, you're just going to ruin the building.
Well, we call that a hospital and an art gallery.
Right. Or moldy. You can call it that too.
I think that all of those are redundant.
Yes, they're sort of implied.
Very good. I want to add one more, and it's a much briefer question from the audience here. Someone asks, I'm working with an architect who insists on covering the mineral wool continuous insulation with a water-resistive barrier, even though no open joints. Does mineral wool need a water-resistive barrier cover?
No. I mean, and clearly
let's have a food fight. Yeah, let's whatever.
So, I mean, if you have a good quality, fully adhered air water barrier behind the rock wool, well, of course the rock wool doesn't need another layer on top of it. On the other hand, since the architect is keen on it, I'm sure they wouldn't mind paying for it. And so, and if they're willing to pay for it, as long as it's a vapor permeable one, knock yourself out. It's good. It definitely improves performance. Is the bang for buck there? On normal assemblies of vertical walls or non-open jointed walls, there's no bang for buck. The moment you go open jointed, it starts to become kind of important. And if you tilt that wall from vertical to 5 degrees off because you have a starchitect, not an architect, then it becomes critical. Then suddenly it becomes absolutely necessary for normal assemblies to work.
Well, you know what Werner Gumpert said, if it's not vertical, it's a roof.
It's a roof, yeah. Well, I agree. I didn't know he said that, but I'm not surprised he's right.
So we're pretty much at time. It has been a privilege to have you both on this webinar for this live discussion. Thank you very much for coming on, for making the time. I think we could go on for much longer, but we scheduled this for 1 hour, so I'd like to wrap it up at this point. For the audience, We will be sending a follow-up email. So if you're an ERMA member, you can get credits for participating in today's webinar, and you can provide your information on the form that will be provided. To wrap this up, I'd like to show you a few more slides to just give you a brief overview of who we are as a company, as a Dörken company. Our products are Delta branded, so every product we make carries the Delta brand, and we can provide a lot of extra service and help. To touch on just a few highlights in our product portfolio, our product Delta Vent SA is a self-adhering air and water resistive barrier, highly vapor permeable, particularly easy in installation because it has a self-adhering edge. So the overlap area is fully adhered into both directions, which creates 100% seal and doesn't require extra treatment like tapes and so on. Products carry health product declarations. So if you design to LEED version 4 standard, we can help out with that. Here an example of an apartment building that carries a self-adhering membrane with lots of window integration. On the open joint facade topic, we have a product called Delta Facade S. It was particularly designed as an air and water resistive barrier, but it has an extremely high UV resistance to be able to expose long-term to these open joints and to the UV light that goes through. Here's an example again, Clippership Wharf in Boston, a multifamily complex. It actually carries both products. Inboard of the continuous insulation, you see the gray layer, that is a self-adhering water resistive barrier, Delta Vent SA. And outboard of the continuous insulation, you see a black layer that is the UV resistant Delta Facade. And then outboard of that, they had phenolic panels with open joints installed. We support Passive House. We have a lot of certified Passive House details available for those who are interested in utilizing these products under those circumstances. For more information, feel free to visit our website, Dörken.com. You'll find all of our products, also the below grades, drainage boards, and so on there. You'll find a lot of installation details and videos and help and support, but we also have a live team here at the office to help with any challenges on particular job sites. You'll find your local representatives in your particular area. You can look up your area and it will show up the direct contact points in the field. And with that, I'd like to draw your attention to another video feature that is coming up. A cup of Joe basically taking a few minutes over a cup of coffee to elaborate on net zero energy houses and beyond. With that, I would like to thank all the expert contributors that have been participating in our Building Science Deconstructed series. This year today was the highlight before we go into the summer break. We'll revamp later in the year, in the fall, but we have been doing this here every few weeks now since March, since the pandemic broke out. And at this point, we want to go into a well-deserved summer break as well. So thank you to all the contributors that have been part of this educational series. A special thanks again to John and Joe for being on the panel today and for making this all happen. It was fantastic to have you and the two grandmasters of building science here on today's webinar. Thank you very much for your time. And a big thank you also to all attendees. I hope you will have a fantastic weekend and be safe.